Hey, ninth graders, we are finishing up our last lesson of our Unit 3. So we've been talking a ton about modeling quadratics, and at this point you might be feeling a little bit tired of modeling quadratics, but I do want you to realize kind of the progression of what we've seen so far this year, right? So we've started at the beginning of this year just discussing factoring, and then we left factoring and discussing radical equations and radical numbers and how to deal with them. And then we left that and said, okay, well then now that we know how to deal with factoring quadratics, how about we take it one step further and we solve for quadratics? And now this third unit is talking about, okay, now we're talking about the graph of a quadratic, the visual representation of a quadratic. And what does it mean when we've solved for a quadratic, right? It means that we've solved for those x-intercepts. Setting it equal to 0 is finding where it crosses the x-intercept, which is really important when we're talking about the real-world application of quadratic equations, of which there are many. Quadratic modeling. Modeling is a mathematical phrase that we use to talk about how we represent a real world situation in a mathematical way. So a model in mathematics would be an equation or maybe a graph of an equation. So quadratic modeling is dealing with modeling any type of real world situation that has some sort of parabolic arch. And that always happens with something that we call projectile motion. So anytime you throw anything, a ball, or anytime somebody jumps, right, and it has that sort of curve, or if we're talking about countries and their defense systems, if they're sending missiles, right, that follows a parabolic arch. So all of these things have this one tie-in, which is that they are all quadratics. And there's all sorts of different ways that we then can interpret what it means to be a quadratic equation and interpret all of these things that we've learned how to find. We've learned how to find x-intercepts, and those are when y equals 0. So then what does y represent? Well, y represents the height of that thing that is jumping, right? And or being thrown. And so when the height is 0 means is when it's on the ground. And so being able to take the mathematical sense of everything that we're learning and applying it in a real world way is very, very important and absolutely going to be something that you see in your maths courses in the future. You're going to be seeing it next year. You're definitely going to be seeing it in your IB classes. For those of you who are curious about difference between applications and analysis, what we're talking about right now, the problems that we're going to be doing in class today, are all applications types of problems. So remember, in IB, you're going to have kind of like two umbrellas to choose from. You're going to have more of like an applications HL/SL type of mathematics or an analysis HL/SL to choose from. And the difference is that applications is applying mathematics in a real world sense. And so the problems that we're doing today are going to be applying mathematics in a real world sense. Versus analysis would be something like giving you a crazy mathematical function with no real world tie-in and just asking you to do the mathematics and understand the patterns that are there. So that's kind of main differences between applications and analysis. And today we're going to take a look at kind of what we think and what we see when we're in an applications type of course. Okay, so when we're talking about a visual representation of a quadratic equation, in other words, a parabola, we are going to talk about a lot of main behaviors, but the first one is that I want to talk about the vertex. So if the parabola opens upward, then the vertex represents, so if it opens upwards, that's what I mean by opening up. The vertex represents a relative minimum. And since it is a parabola, it's the only minimum, so we could just call it the minimum, but we could also call it the relative minimum. If a parabola opens downwards, then the vertex represents a relative maximum. I do want you to pay attention to one thing, that when we're talking about maximizing a quadratic, we're actually only talking about maximizing or minimizing one variable. All of our equations that we've talked about so far in this class have all been of two variables. You can have three variables when we talk about three-dimensional graphing, but right now all we've been talking about is two-dimensional graphing, which means we're talking about two variables. When we're talking about the maximum or the minimum of a graph, what we're talking about is the maximum y value. It's not the maximum x value, because realize that we can go bigger on that x value. We're talking about when is it at its highest, when is it at its lowest. And so this is the y's maximum and the y's minimum. And that's really important to keep in mind as we're applying this to the real world situation. Because now it won't always be y, it'll be something else, maybe a different variable, right? T of t. This is now your y. So we're trying to maximize or minimize this variable, uppercase T, degrees in Celsius, not lowercase t. Okay, so that's something to keep in mind as we're applying this. Okay. Last weekend, Mr. Quilty decided to go winter camping in the Dolomites. His body temperature, capital T in degrees Celsius, is given by this equation, where lowercase t represents the hours after 9 p.m. I do think it's important on problems like these to label. I know it says what your variables are, but just really quickly, just for you to solidify it in your brain, but also as a quick reference point, write down capital T equals temp in degrees Celsius, lower t equals hours, and specifically after 9 p.m. That's important. We'll talk about it later, but keep that in mind. Specifically hours after 9 p.m. So if lowercase t equals 1, then we're talking about 10 p.m. If lowercase t equals 3, then we're talking about 12 a.m. What was Mr. Quilty's body temperature when he woke up to pack out at 8 a.m.? So first we need to think about how many hours afterwards. So if 9 p.m. to 8 a.m., that is one less than a 12-hour cycle. So that's 11 hours after 9 p.m., right? So 12-hour cycle would be 9 a.m., but this is 8 a.m., so it's one less than a 12-hour cycle, and so it's 11 hours. One way to kind of think about it, which means that this is our lowercase t. So we're going to plug in 11 for our lowercase t and solve for uppercase t. I don't think you need me to explain how to plug in t of 11. So I would like for you to find it for me. You should have gotten, I'll go ahead and use an approximate symbol because this is no longer going to be exactly equal because I'm rounding to 2 decimal places. 36.78 degrees Celsius. So that would have been our answer there. So just evaluating the quadratic, which we've been doing this whole unit anyway. Now we're just applying it in a real world situation. At what time was his body temperature minimized? So we do know that this is a minimum because we see that this A value right here is positive. No matter what, even if it's a fraction, if it's positive, it's going to open up. If it's negative, then it's going to open down. So since A is greater than 0, vertex is a minimum. So at what time was the body temperature minimized? So we're actually here talking about the vertex. Specifically, what time is saying the x value or lowercase t value, right? Because that time is what's on the x-axis. So we're trying to figure out at what x value or lowercase t value do we have a minimum in our y value or uppercase t. So this is talking about our vertex, and we have a formula for discussing the x value of a vertex. The x value of a vertex is negative b over 2a. This formula is really helpful when we're talking about real world situations because notice real world situations don't always have nice numbers. In regards to real world situations, that's actually probably about as nice as it's going to get. So it's important to have a formula so that way you don't have to worry about factoring or turning it into vertex form. I definitely do not want to complete the square on that guy. That seems ridiculous. So I'm going to go ahead and use this formula. And by that, I mean you're going to go ahead and use this formula. So go ahead and tell me what that lowercase t value is that would minimize Mr. Quilty's temperature. Going ahead and plugging in b, which is negative 4/3, it becomes negative 4/3. So that's 4/3 divided by 2 times a, which is 1/9. Remember that fractions are ultimately just division problems in disguise. So I'm going to turn this into 4/3 divided by, I'm going to multiply these guys together, and they are 2/9. I know dividing fractions becomes copy dot flip flops, or however, whoever taught that to you, copy dot flip or keep change flip. But you keep the first fraction, you change that division to multiplication, and you flip that second fraction. I could even simplify before I multiply. That 4 and 2 simplify down, the 3 and 9 simplify down, and I'm left with 6. However, that is not our final answer, because we want to know at what time was his body temperature minimized. And this is 6 hours after 9 p.m. So what is 6 hours after 9 p.m.? Well, 3 hours would get us to 12 a.m. and then another 3 hours would complete our 6 hours that we have. So that would be at 3 a.m. Right? So if we're talking about 6 hours, I first want to get to the end of the day, because that's how my brain makes sense of how to add time in this weird modular mathematics that is our 24-hour time cycle. So I want to get to 12 p.m. and that gives me 3 hours to get me to 12 p.m. And then I have a leftover of 3 more hours to complete the 6 total hours, which results in 3 a.m. And that, my friends, is the final answer, not 6. So that is why it's so important to keep in mind what your variables are and what their units of measurement are. So now that we have that at lowercase t equals 6 is when our vertex is, we want to know what was his minimum temperature. So we want to know what the temperature was, so capital T equals question mark, when lowercase t equals 6. Notice that before every single problem, before I've asked to solve for it, especially with word problems, I write out a few things. I write out a few things that help guide me. I do this even when I'm just doing mathematics on my own. It's so important to label your variables, to make connections and underline things in the question, to show out your work. Write out a prepared step. Okay, I'm solving for this when this is that. There's so many other things you have to think about. Put down things on the paper so you don't have to think about them anymore. So you can only think about what the actual mathematics that actually are happening in the moment at that time. Okay, go ahead and solve for t of 6. T of 6 is 34, which means that Mr. Quelty's minimum body temperature was 34 degrees Celsius. We then want to find the y-intercept. This would technically actually be your uppercase t-intercept, because your graph is no longer x versus y, it's lowercase t versus uppercase t, right? So if we had some sort of parabola like this, and here we would have 6:34, 6 hours after 9 p.m., a minimum temperature of 34, we are now talking about that y-intercept.